Good morning, all of you, wherever you are. I hope you are doing great. Last video, we discussed about some of the applications of Gauss's law. In this video, we shall discuss a very important concept. We will see what is an electric dipole. So far, whatever we have discussed, it constitutes, I would say, electric monopole. Electric monopole. Even though we don't use explicitly the statement or the name monopole, so we have discussed about positive charge, negative charge alone. That's nothing but electric monopole. In this class, we shall discuss about combination of these two entities, positive and negative charges, electric dipole. We will see whether it has got any reasonable electric field and why we need to study about electric dipole. So let's get started with a few definitions. So what is an electric dipole? One of the most important charge distribution, I would say, is electric dipole. Why we are excessively worried about electric dipole? Because many molecules that naturally occur, they have this dipole structure. For instance, water molecule, it it is possessed or endowed with a dipole structure, and molecular modeling becomes that much easier when you start appreciating the electric dipole. So how do you define an electric dipole? Two point charges, positive and negative, having the same magnitude but opposite polarity and separated by a distance. Even the magnitude doesn't matter here. Two point charges having different signs separated over a distance constitutes an electric dipole. So let's look at an example. You can see here the map of an electric dipole. You have a positive charge which is plus 5. You have a negative charge which is minus 3. Now these are the electric field lines. The electric field lines, they originate from positive charge because that's the convention, and they end up on the negative charge. Now if you carefully look at these electric field lines, you can observe one thing. The thing is, at close distances, the field lines are a lot closer. You can see that this field line is closer, this field line is closer. But when you extend this electric field line over long distances, they drift away. You can see there is a clear drift between this particular field line. You can see this electric field line spread out. So the idea is, when you go far away from an electric dipole at long distances, in other words, the electric field lines appear as if they are radial. Now, have we encountered this kind of a radial distribution of electric field lines? Yes, of course. The point charge or the electric monopole, the field lines, electric field lines of an electric monopole, whether it is positive or negative, it doesn't matter. It resembles a radial distribution. Now, sometimes you can see here the net charge, the electric charge on a dipole is 0. Supposing we have a couple of charges, one is, let us say, plus 1, the other one is negative 1, then the net charge here, it has to be 0 if you sum up the electric field. But if you sum up with these two charges, I'm sorry, but the electric field is not 0. The electric field is being felt, and that is where the whole thing becomes interesting. The next question we need to ask ourselves is, can we calculate this electric field? Yes, of course, we can calculate the electric field. So that's what exactly we are going to do in this video. So we are going to see what is the electric field of a dipole along the axis of a dipole. Then in the next video, we shall see how it, whether we can compute the electric field on the equatorial point. Now let's take the first example. We are going to calculate the electric field away on the axis of the dipole. Now this is the axis of a dipole. You have a dipole plus q and minus q separated over a distance d, and then there is a point P, and this point P is so far away from the dipole. That's the reason why I put a lot of dots over here. The distance from P to minus q is r. Now here anybody can ask this question, why specifically minus q? Why can't you have plus q? Or why can't we take this particular point at the center of the dipole? From here also we can mark it as r. Yes, of course we can do it. But please remember, the more we go away from a dipole, it doesn't really matter whether we take the distance from minus q, whether we take the distance from plus q, it hardly matters. So in this example, what I have done is I have reckoned to be the distance is reckoned to be from the negative charge to this particular point P. Now let's say what kind of an influence, let's think about what kind of an influence these two charges individually have at this particular point. Now if you plot the electric field which is due to this charge minus q, you can see that the electric field lines will be running towards this charge minus q. So this is E minus. Now if you try to understand the influence of plus q on P, you can see that the electric field line will be away from this particular point P. That is, this is due to plus q and this is due to minus q. So how do we map the net electric field at P? The net electric field at P is primarily decided based on whether it is minus q or plus q over here. We have this minus q over here, so which is a little bit closer to the point P. So this net electric field is mapped as if it is pointing towards minus q. Now let's calculate the electric field. So we want to calculate the net electric field. So the net electric field is written with a very simple equation. We are going to use the superposition principle. It's going to be E minus. In this case, since the direction of E plus is opposite, we write minus E plus. You know what is E minus, which is kq by r square. The distance is r square. However, E plus is minus kq divided by r plus d the whole square. So let's calculate this. So this is not very difficult. So you just take kq as the common factor, and you can take this as the common denominator, r square r plus d the whole square. Now here we will be getting r plus d the whole square minus r square. So once again we can put kq. So this is going to be r square plus d square plus 2rd minus r square the whole divided by r square r plus d the whole square. So you can cancel the positive r square and the negative r square in the upstairs. Now we are left with this equation. Now remember, this d is the distance between these two dipoles. So you have this plus q and the minus q. So this is separated at a distance d. Now this d is much lesser, I should say, than r. R is very much greater than d. So what we can do is we can eliminate this d. D is always, d square is always going to be close to 0. So you can eliminate the d from this equation. So we are going to get 2rd in the numerator, and here too you can take this d out of this equation. So you will end up getting r power 4 in the denominator. You can cancel r both upstairs and downstairs. Then you get kq over 2d by r cube. So this is going to be your net electric field. Now let's deviate a little bit here. There is another one important quantity which defines an electric dipole, and that's a vector quantity called electric dipole moment. Electric dipole moment. It's given by the symbol P and it's a vector quantity. Now electric dipole moment is always used to describe an electric dipole essentially at long distances. So electric dipole moment is defined as the product of the charge and the distance, product of the magnitude of the charge, I should say, with the distance. And it is a vector quantity, and the electric dipole moment is such that it is always directed from negative to positive. This is the direction of the electric dipole moment, always running from negative to positive. Now it is a vector. Why it is a vector is the orientation of a dipole is also important when it comes to calculating the electric field. We have here calculated the net electric field along the axis. In the next video, I'll show you how to calculate the net electric field at an arbitrary point P lying on the equatorial line. There the electric field will change. So orientation becomes important. When the orientation becomes important of a dipole, the electric dipole moment necessarily should be a vector. Now we need to modify this equation. E net here is going to be, you can comfortably write this Q and D as P. So we will be getting here 2 kp over r cube. Now these are vector quantities, electric field and electric dipole moment. Now we saw in the diagram, I'll come back to it. You can see here that the net electric field is pointed towards the negative charge, and the electric dipole moment is also running from negative to positive charge. That's what I said. So here the electric dipole moment and the net electric field are in the same direction. So it's very simple for us. We can write that E net, which is a vector, is always equal to 2 kp over r cube. Now the difference between a point charge and a dipole is, you can see here that the electric field for a dipole, let me put di here, is inversely proportional to 1 over r cube. Whereas if you take the point charge into consideration, the electric field for a point charge is 1 over r square. So that's the difference. So at long distances, the electric field due to a dipole becomes more weaker than compared to a point charge, and that's what we need to understand. This is all about dipoles now. In the next video, we shall calculate the electric field for a dipole, for a point P lying on the equatorial line of the dipole. Thank you.